delta difference, small but finite. Concept clarity. Under this category of delta difference videos, here we discuss dynamics of pure rolling. Let us consider a rollable rigid body that could be a sphere or a cylinder or a ring or a disc placed on a hard surface. We're talking of a hard surface, that's very important. And this is a perfect rigid body. When we say this, what we mean to say is we are going to ignore the deformation produced near the contact, because if the deformation is considered, the modeling will be slightly complicated. And physics is science of approximations. A real system will have many factors affecting it. So to discuss that situation, it's not so easy. Therefore, we approximate and then of course superpose to get the actual situation. For the present, as I told you, we are considering a hard surface. That means when that body is placed on it, there's not going to be any depression in the surface or any deformation in the surface, any dent in the surface. And similarly, there is no deformation even in the rigid body. Now, for such a rigid body, we just deliver a blow here. Delivering a blow is, in physical terms, is providing an impulse. And let me just remind, this surface is a rough surface. We delivered a blow here. Probably this could have been a billiard ball which is hit by the cue through the center of mass. Once this is done, the ball will simply jerk into motion like that. And because you're delivering the blow through the center of mass, this whole body moves as one piece. In doing so, it rubs against the surface. Since this is a rough surface, friction develops. This friction developed is simply kinetic friction, because you have already given it a blow, which means you have not given a chance for static friction to develop and then kinetic friction to develop. At one go, the body was put into motion and it is rubbing against the surface, whereby Fk immediately develops. This happens in a very, very short while. So we are not taking the body slightly forward there. So let us think for a while that impulse is applied in a very, very short duration, and therefore friction almost immediately developed there. But remember, when the impulse was developed, the body which was initially at rest would get a speed like this. We may call it some V0, for example. In physical terms, when you want to write this in physical terms, you write F into delta T is equal to m V0 minus 0. Remember, this F will be not acting anymore on the body. Once you delivered the blow, the body had just taken off with velocity V0, that is center of mass velocity V0, and no more that F is acting. That's the meaning of actually impulsive forces here. Now, this V0 was given to the body. So what will happen now? This Fk, the kinetic friction, will reduce Vo, that is velocity of center of mass. But at the same time, this Fk would produce a torque about the center of mass. I am taking the radius to be r. Fk into r will produce a torque, and this will start increasing the angular velocity in this direction. So what is going to happen now? The Fk will keep on decreasing the center of mass velocity. I'll draw the sphere again somewhere here. By this time it comes here, for example, the velocity of center of mass would be something lesser than the original V0, but there will be one omega here which was not there at all previously. So what is going to happen near the point of contact? Because of the center of mass motion, the body will be moved as a whole this way, the point of contact will be moved this way, but omega r, the tangential velocity, makes that point of contact go this way. So this VCM and this omega r, this is the velocity with respect to center of mass, you see. That means somebody watching from here will say that the edges of the body have omega r tangentially like that. But at this point of contact, this omega r and that VCM will be opposite to each other. So what is happening? VCM is decreasing, omega r is increasing. Now I'll extend this surface a little. What is going to happen? This keeps on happening for some time, and somewhere later there the reduced VCM, here I'll call it V final for a while, and the increased omega final into r become equal, and since they were opposite to each other here, because they were opposite to each other here, when they become equal, that is when V final is equal to omega final into r, the point of contact has zero velocity. Zero velocity for whom? For a person watching from the surface. And we know already that this is what we mean by pure rolling. The body's point of contact, which is in touch with the surface, if it has zero velocity, this will not slide here, or as people say, this acts like a point through which the body can be thought to be only rotating. The instantaneous axis of rotation passes through this point, people say. That we'll discuss later. But right now, when this V final becomes equal to omega final into r, this point of contact stops moving. And of course, as the body moves, every time a different point comes into contact, but at every instant, for a person watching from here, this point will be at rest. There will be no sliding happening at all. And this is what we mean by pure rolling. That means this V0 will come to some other lesser value, and omega final r will be having a higher value, and those two things become equal, and this point instantaneously comes to rest, and pure rolling is going to happen. That means as the body rolls now, rolling is translation of center of mass plus rotation about center of mass, as we know. So this keeps happening, and the body will be continuing to pure roll forever. Why? You got some V final, you got some omega final into r, and since the point of contact has come to rest, this kinetic friction, whatever was there, will disappear. So there's no more force acting on the body either to produce a torque or to produce a force. So the center of mass velocity doesn't change, omega final into r doesn't change, so the body continues to pure roll forever. But remember, All this is true because we considered a hard surface and a perfect rigid body. And look, once this starts pure rolling, even if it now gets onto a smooth surface suddenly, it will still continue to pure roll. Because, like I told you already, once pure rolling started, friction disappeared. So, Newton's law says, unless there's a force acting, there's a torque acting, the situation doesn't change. So, once it, even if it goes onto smooth surface, you don't require any friction now to sustain the pure rolling. So, the pure rolling goes on happening forever. But in practice, remember, a rolling body like this, which is given an impulse and set to roll, will practically stop. That's for a different reason, which we'll be addressing in a different video. But let me tell you one more thing before we conclude. This friction was acting until the pure rolling started. There's a kinetic friction. So some kinetic energy would be lost in the form of heat, in the form of unorganized random motion of the kinetic energy of the molecules on the surface and as well the body. That means when you touch them, they'll be slightly heated up. So kinetic energy will be lost until the pure rolling starts. Of course, to further elaborate it and convert into problems, we'll go for another video. Thank you.